On August 6, 2025, the James Webb Space Telescope turned its infrared eye toward a visitor that had only been on Earth's radar for 5 weeks, and within hours of processing the data, the scientists running the observation knew something didn't add up. Not a glitch, not a calibration error, a real, repeatable chemical signature coming off an object that had traveled here from another star system entirely, and it was producing a ratio of gases that comets in our own solar system essentially never produce. This is the story of 3I Atlas, only the third interstellar object ever confirmed passing through our solar system, and the one specific measurement inside its data that astronomers still can't fully explain. A signature so far outside the normal range that it forced a published research team to say, in plain terms, that this object simply doesn't chemically resemble anything born in our own cosmic backyard. Here's why an object like this is such a big deal in the first place. Every comet and asteroid inside our own solar system, no matter how strange it looks, formed from the same original disk of gas and dust that also built the sun, the planets, and everything else orbiting out to the Oort cloud. That means even the weirdest solar system comet is still fundamentally made of leftover material from our own cosmic neighborhood. An interstellar object is different in kind, not just in degree. It formed around a completely separate star, in a completely separate protoplanetary disk, light years away, and then got gravitationally flung out of that system entirely, flying through interstellar space for what could be hundreds of millions or even billions of years before, by sheer chance, passing close enough to our sun for us to notice it at all. Astronomers had theorized objects like this should exist for decades before ever actually catching one. Oumuamua, spotted in 2017, was the proof that the theory was right, but it moved so fast and was found so late in its approach that telescopes barely had time to gather data before it was gone, leaving behind more open questions than answers, including its own genuinely puzzling acceleration that briefly fueled the same kind of speculation now surrounding 3I Atlas. 2I Borisov, found in 2019, behaved much more like an ordinary comet chemically, which was reassuring in its own way. It suggested that interstellar comets might not be as alien, chemically speaking, as some had feared. 3I Atlas is only the third confirmed case in all of recorded astronomy. And this time, thanks to earlier detection and a fleet of modern instruments, including Webb, scientists actually had the tracking time and technology to study it properly before it disappeared again. Before getting into what Webb actually found, it's worth being clear about what 3I Atlas is, because this isn't speculative content built around a grainy photo. It was discovered on July 1st, 2025, by the Atlas Survey, short for Asteroid Terrestrial Impact Last Alert System, a network to scan the sky for exactly this kind of object. Its trajectory was unmistakable from the very first tracking data, moving too fast, on too steep a hyperbolic path, to have originated anywhere inside our own solar system. That made it only the third confirmed interstellar object in recorded history, following 1I Oumuamua in 2017 and 2I Borisov in 2019. Once its interstellar origin was confirmed, nearly every major observatory available turned toward it. Hubble, the Swift Observatory, the Sphere-X mission, and eventually the James Webb Space Telescope, which observed the object on August 6th using its near-infrared spectrograph, or NIRSpec, an instrument built specifically to break incoming light down into its exact chemical fingerprint. The resulting findings were published as a peer-reviewed paper in the Astrophysical Journal Letters by a research team that included NASA and European Space Agency scientists. So what follows isn't fringe interpretation of a blurry image. It's a formally published chemical analysis of light collected from an object that formed around a star that isn't our own. Here's what Webb was actually looking for. As comets approach the sun, the heat causes frozen material on their surface to sublimate directly from solid to gas, forming a glowing cloud around the nucleus called a coma. That coma is essentially a chemical signature of whatever ices the comet is made of. And for the thousands of solar system comets astronomers have studied over the last century, that signature follows a fairly predictable pattern. Mostly water vapor, since water ice is the dominant frozen material in the vast majority of comets that formed inside our own solar system, with smaller, more variable amounts of carbon dioxide, carbon monoxide, and trace gases mixed in. 3I Atlas did not follow that pattern. When Webb's NIRSpec data came back, the coma wasn't water-dominated at all. It was overwhelmingly carbon dioxide, alongside detections of water, carbon monoxide, water ice, dust, and a tentative signal of a sulfur compound called carbonyl sulfide. Specifically, researchers measured the ratio of carbon dioxide to water at 7.6 to 1, meaning for every molecule of water vapor detected, there were more than 7.5 molecules of carbon dioxide. That number isn't just unusual. According to the published analysis, It sits about 4.5 standard deviations above the established trend line for how comets in our own solar system typically behave at that same distance from the Sun. A statistical gap large enough that in most areas of science you'd assume you were looking at a measurement error before you'd assume it was real. Except this measurement has been checked, cross-referenced against earlier detections. From the Sphere-X mission that had already flagged unusually high carbon dioxide activity, and it held up. This is the detail that doesn't make sense. Not because it breaks the laws of physics, but because nothing in our own solar system's comet population prepared scientists to see a ratio this extreme. So why would that happen? The leading explanation astronomers have offered comes down to where and how cold this object originally formed. Water ice and carbon dioxide ice condense out of a gas cloud at very different temperatures. Water ice can form in relatively warmer regions of a young star system, while carbon dioxide ice only becomes stable at much colder temperatures, further out from a star, where the environment barely ever warms up. Think of it the way frost forms differently depending on how cold a surface actually gets. A mildly cold night might leave a light layer of dew, but only a genuinely deep freeze locks in a thick, stable layer of ice that doesn't melt off again. Carbon dioxide needs that same kind of deep freeze to stay locked into a solid rather than evaporating away, meaning it can only accumulate in the coldest, most distant regions of a forming star system. A coma, this dominated by carbon dioxide, suggests that 3I or Atlas may have originally formed in an extremely cold outer region of its home star system, far enough from its star the carbon dioxide ice could accumulate and dominate the object's composition in a way it rarely does for objects that formed closer in, the way most of our own solar system's comets did. In other words, the ratio isn't just a weird number, it's a fingerprint pointing back at conditions in a completely different planetary system, one that may have had a much larger, colder outer zone than our own solar system does. There's a second layer to this that makes the story even stranger. The coma wasn't just chemically lopsided, it was also asymmetric in shape, with outgassing noticeably enhanced on the side of the object facing the Sun, rather than spreading evenly in all directions, the way a more typical comet's activity often does. Combined with earlier measurements from the Jewett team estimating the nucleus at an effective radius under 2.8 kilometers, losing dust at a rate estimated between 12 and 120 kilograms per second, the picture that's emerging is of a compact ancient object venting an unusually specific mix of gases in an unusually specific direction, which is exactly the kind of data set that keeps a science team running the numbers over and over, instead of simply filing the observation away. That asymmetry matters just as much as the chemistry itself, because it tells researchers something about the object's structure, not just its ingredients. A perfectly uniform coma would suggest a nucleus with a fairly even, well-mixed composition all the way around. An asymmetric one, concentrated toward the sun-facing side, suggests pockets of material distributed unevenly across the surface or just beneath it. Patches of especially volatile ice that only start venting once direct sunlight reaches them, while the rest of the nucleus stays comparatively inert. That kind of patchiness is consistent with a surface that's been through billions of years of cosmic radiation exposure during its long journey through interstellar space, slowly baking and altering the outermost layers, while material deeper inside stayed protected and largely unchanged, effectively preserving a partial time capsule of its original composition underneath a heavily processed outer crust. Let's pull that together for a second before going further. 3I, Atlas, is a confirmed interstellar object, only the third ever recorded, observed directly by the James Webb Space Telescope using peer-reviewed spectroscopy. Its coma is dominated by carbon dioxide at a ratio to water that's statistically abnormal, compared to essentially every comet ever measured inside our own solar system. And the leading scientific explanation is that it formed in an unusually cold, distant region of a star system that isn't ours, meaning this single measurement may be the closest astronomers have ever come to directly sampling the chemistry of another planetary system's outer edge. That's already a remarkable result on its own. But it's also exactly the kind of unresolved anomaly that tends to attract interpretations far beyond what the data itself supports. And that's worth addressing directly, because there is a more sensational version of this story circulating, and it deserves a clear-eyed look rather than a dismissal or an endorsement. Harvard astronomer Avi Loeb, known for previously suggesting that Oumuamua could have been artificial technology rather than a natural object, has pointed to 3IR Atlas's unusual mass, its jet-like glow, and reported detections of nickel in its spectral data as reasons to consider whether the object might be something more complex than an ordinary comet. It's worth being precise about what's actually established here versus what's speculative extrapolation. The carbon dioxide anomaly is a peer-reviewed, independently corroborated measurement. Claims tying that data to an artificial or technological origin are not part of the peer-reviewed consensus. have not been supported by the broader community of astronomers and planetary scientists analyzing the same dataset and represent one individual researcher's interpretation rather than an established scientific finding. The overwhelming majority of scientists working on this object, including the JWST research team that authored the primary published paper, described the 3I Atlas as a natural comet with an unusual, scientifically valuable chemical signature, not an anomaly requiring an exotic explanation. Extraordinary claims deserve real scrutiny, and right now, the extraordinary explanation isn't the one carrying the evidence. It's also worth noting that some of the most viral claims attached to this object online, descriptions of detected methane signatures, extreme heavy water ratios, or an object dated to 10 to 12 billion years old confirmed in nature, go well beyond what has actually been published in the peer-reviewed record as of these observations, and should be treated with real skepticism, regardless of how confidently they're presented in a headline or a thumbnail. This is a useful pattern to recognize whenever a genuinely rare scientific event goes viral. The real, sourced measurement travels through a chain of secondhand summaries, each one adding a little more drama than the last, until the version circulating on social media barely resembles the modest, carefully worded conclusion in the original paper. The verified story here is dramatic enough without embellishment. A chemical signature from beyond our solar system measured directly that doesn't match anything we've cataloged from thousands of comets born right here at home. 3I Atlas made its closest approach to the Sun in October of 2025, and it's now on its way back out of the solar system for good, never to return, carrying with it a chemical record of wherever it originally formed. Light years from here. Every telescope that got a look at it before it left added one more piece to a puzzle that, right now, remains genuinely unsolved. Not because the answer is unknowable, but because it's the first real chemical sample we've ever collected from a comet that didn't grow up around our Sun. The most honest way to describe where the science currently stands is this. Astronomers know exactly what they measured. They have a solid working theory for why it looks the way it does, and they are still working out precisely what that means for how planetary systems very different from our own take shape. That's also, in a strange way, the appeal of a story like this one. Not a tidy, fully solved mystery with a clean ending, but a real ongoing scientific process, playing out in published papers and follow-up observations rather than in a single dramatic reveal. So here's the question worth sitting with. If the leading explanation holds up, that 3I Atlas formed in an extremely cold, carbon dioxide-rich region of a distant star system, what does that tell us about how common, or how strange, our own solar system's formation might actually be compared to everywhere else in the galaxy? It's a question astronomers will likely spend years chasing, long after this particular visitor has faded back into the dark it came from. Let me know what you think. Down in the comments, and if unresolved space mysteries like this one are your thing, there's more waiting for you right here.